also, a role will be played by a certain division algebras with center K, so I will let Dn be the division algebra center K with dimension n squared, and there are Euler phi function of n of such things, and I want to take the specific one which has Hasse invariant 1 over n. And then, perhaps most importantly, the absolute Galois group of K. All right, G for the Galois group of the algebraic closure of K over K. And it comes, in fact, I'm going to want certain variants of this group, so let me quickly remind you about what they are. The absolute Galois group of the local field comes with a natural surjection to the absolute Galois group of its residue field. And the kernel is, of course, the inertia group. And the Galois group of the finite field, of course, is a very simple structure. It's procyclic with a canonical generator. And Frobenius, and I'm going to take the geometric Frobenius for definiteness, maybe the inverse of the natural one, so the Frobenius element acting on something in the residue field raised to the cardinality of the residue field gives you the element itself back. And let me just take the discrete group generated by this, a copy of Z, which sits inside here as a dense subgroup. And then it will be convenient to work with a slight variant of the absolute Galois group known as the Weil group. Which is just the preimage inside the Galois group of the integer powers of the Frobenius. So it's a dense subgroup of the whole Galois group. I'm given a topology so that this is the inertia group is an open subgroup of the Weil group. For those of you who are not familiar with the Weil group, you don't lose much by always thinking of it as the Galois group. But it's got slight technical advantages. As some motivation for what we're going to do, let me just remind you about local class field theory. Main theorems of this were established by Hasse in about 1930. In a sense, the main result of local class field theory is that there's a natural isomorphism from the multiplicative group of non-zero elements of the field to the abelianization of the Weil group. The Weil group modulo the closure of the subgroup generated by commutators, the maximal continuous abelian quotient of the Weil group. And it's not just a simple isomorphism, it comes with of abstract or topological groups, it comes with a lot of other structure. You can read off, the Galois group comes with a lot of higher ramification structure, so particularly you can read off the higher ramification structure here in terms of simple things over here. So there's some control over ramification. There are certain functorialities, most particularly compatibility with the norm. If you have a finite extension L over K, the natural map from the abelianized Weil group of L to the abelianized Weil group of K is the same as the norm map on the multiplicative group of the fields. And it's also compatible with various global instances of global class field theory. So some global compatibilities. And all these somehow crucial to this being a useful isomorphism is the fact that behind it there are all these other things. In fact, Hass's proof was a global proof. Hasse, global class field theory was being developed in the years leading up to Hass's work, and then he realized you could deduce from it these such local statements. Later, in 1950s and onwards, the purely local proofs were found of these results. And I wanted to mention that what will appear a rather stupid, in this case, reformulation of this, I've got an isomorphism between abelian groups. Another way of putting it is that there's a bijection, natural bijection, between the one-dimensional or irreducible representations of those groups. So there's a natural bijection between irreducible representations of the multiplicative group of the field, which is just GL1 of K, is naturally in bijection with, well, if you like, the one-dimensional representations of the abelianized Weil group, but that's just the one-dimensional representations of the Weil group. Okay, and the map is the obvious one. It sends a representation here to pi composed with the inverse of this isomorphism. I call this art. It's usually called the Artin map. So this is usually thought of as something telling you about what's essentially the Galois group, giving you information about this. But I guess you could think of it as also, seem a bit perverse, but you could think of it as giving you information about the irreducible representations of K-cross, so there's nothing so mysterious about that in this case. Okay, so the dual problems I want to discuss are, on the one hand, this tells you about the abelianization of the Weil group. What about the rest of the Weil group? So describe in some way the whole of the Weil group or the Galois group, along with all these sorts of things, in particular, plus this ramification structure. And on the other hand, to describe the representations, not just of GL1 of K, but of, when we wanted to work in great generality, the K points of any reductive group. Little is known in that generality, so let me just stick to describe the representations of GLN of this group K. And it was realized by Langlands the answers to these two questions are very closely connected, that you can answer either of them, in a sense, with reference to the other one. So certainly my predilection is to think of this as the question that interests me most and hope that a relation with these will shed some light on it. But I guess in the spirit of this conference, in this talk, I'm going to concentrate on the right-hand side. And, this will just come in as it needs to. Okay, so I want to describe, as I say, the representations, try to describe the representations of GLN of one of these p-adic fields. I should first of all tell you which representations I'm going to look at. So we're going to look at smooth. So pi v is a smooth representation of this group if, well, first of all, V is some vector space, say over the complex numbers, and this will usually be infinite dimensional. And then if pi is just a representation of this group on here, so pi maps GL n k to the linear automorphisms of V, homomorphism. But because we're working often in infinite dimensions, we need some continuity sort of condition, and the simplest one can hope for is such that for all vectors in V, their stabilizer in GLN of K is open. So if I had more time, I would try and say a bit about the whole category of smooth representations. For lack of time, I'm going to immediately restrict my attention to irreducible smooth representations. Irreducible just means the obvious thing, that there's no subspace which is invariant by the action of GLN of K. And I'm going to need some sort of coarse information and classification of such representations. So within the irreducible representations, there are first of all the ones that are called square integrable or quasi-square integrable. Irreducible square integrable representations. And within those, there are the ones called cuspidal or supercuspidal. And the simplest way to quickly give a definition of these is via what's called matrix coefficients. So if you have V in the space V and F in its smooth dual, just a linear form on V, which with respect to the dual representation on the dual is a smooth vector, has open stabilizer, then the corresponding matrix coefficient is the map from GLN of K to the complex numbers that sends G onto F of GV. So if these were finite dimension and you chose bases, this might be an entry in the matrix giving the representation. And then square integrable representations are just those where the matrix coefficients are square integrable, at least modulo the center. So these have to be square integrable modulo the center. And the cuspidal representations are just those where the matrix coefficients have compact support modulo the center. So when these matrix coefficients are well behaved, somehow some of the sort of very basic representation theory is easy to carry out. So in some ways, these behave much more like the representations of finite groups. Okay. So I need to, there's one other, before I talk about this correspondence, there's one other result I want to talk about concerning these irreducible smooth representations, and that's the Jacquet-Langlands correspondence, because it will come into our story from time to time. So for GL2, this was established by Jacquet and Langlands. I'm not sure, I guess sometime in the 70s. Then it was generalized to GLN by various people, Rogalski and Delin, Kazjan and Vigneras in the early 80s. And it says the following, that as well as considering representations of GLN of K, I can consider representations of the multiplicative group of this division algebra, or indeed any other division algebra, but I'm going to concentrate on this one. And it says there is a natural bijection, which I will call JL, Jacques Langlands, from the irreducible smooth representations of the multiplicative group of this division algebra to the irreducible square integrable representations of GLN of K. And one way of saying what natural means is that it's defined by a natural, characterized by a natural trace identity. Not only does it satisfy, but this completely characterizes it, that if I take a irreducible let me mention quickly that because this group is compact modulo the center, the irreducible smooth representations here are all finite dimensional. Might lead one to hope that somehow they were easier to study than the infinite dimensional objects over here, though that doesn't seem to be the case. Okay, so let me take an element G, GLN of K, regular semisimple, regular meaning distinct eigenvalues, semisimple meaning semisimple, then if I take rho something in here, apply the Jacques-Langlands correspondence to it, take its trace, whatever that means for an infinite dimensional representation, and evaluate it at G, which is something you can do, then you just get basically the same thing as the trace of rho, which is something you know what it means because we've got a finite dimensional representation of essentially the same element. Well, sorry, I have to divide two cases. Essentially the same element G if G is elliptic, meaning that the characteristic polynomial is irreducible over K, because we're regular, G elliptic. And then there's an element, this G in inverted commas is the element of Dn with the same characteristic polynomial, and 0 if G is not elliptic. Okay, so there's a natural correspondence between these finite dimensional representations of the multiplicative group of the division algebra and the irreducible representations of GLN of K. But the only proofs of this fact are global. They all go via the trace formula. Well, I can't argue with those people in front of us. No, I won't argue. Okay. So what did I want to say next? Okay, so now I wanted to talk about the correspondence with the representations of the Galois group. So the theorem, which is what's called the local Langlands conjecture, first proved by Michael Harris and myself, and shortly afterwards Guy Eniard gave a much simpler proof, says the following. So there is a unique set of bijections, which I will call rec for reciprocity, from the irreducible smooth representations of GLN of K to basically the n-dimensional representations of the Weil group. Let me, for the moment, just write the correct thing, what I hope is the correct thing, and then I will explain it in a few minutes. So basically n-dimensional representations of the Weil group. So n-dimensional Frobenius semi-simple, what I call Weil-Delin representations of the Weil group. Other people tend to call them representations of the Weil-Delin group, satisfying a series of hypotheses that, so in some sense, say that this is a natural bijection. So, for instance, when n equals 1, when n equals 1, we just get the thing we had before from local class field theory. The reciprocity map applied to pi is pi composed with the inverse of the Artin map. The reciprocity map composed with, if I have pi, I can always tensor it with a one-dimensional representation of a GLN, which is always of the form a character composed with the determinant. That's the same as the reciprocity map applied to pi, tensored with reciprocity map applied to chi. The determinant of the n-dimensional representation, which is the reciprocity map applied to pi, should just be the reciprocity map applied to the central character of pi. It should be compatible with joules. And then most importantly, you can define L and epsilon factors for objects on both sides, and these should be the same. So let me fix, probably I should have done that at the start, fix psi max k C cross a non-trivial additive character. Then we want that the L factor associated to a pair of representations on different GLN1 and GLN2 of K should be the same as the L factor to the Galois representation, which is the tensor product of the reciprocity map applied to pi 1 with the reciprocity map applied to pi 2 S, and the same thing for epsilon factors. So this is easy to define. It's basically the characteristic polynomial of Frobenius on the inertial invariance of this, what's basically a Galois representation. This is hard to define. You can define it when these things are one-dimensional, and then you require that it's compatible with change of field by induction, at least induction of things that sit in degree 0. And there's therefore there's at most one thing that satisfies that. It's rather hard to prove that one exists. Deligne gave a global proof of that fact. So that's this one. These two things, I have no idea how they were defined, but they were defined by, I believe, Jacquet, Piatetsky, Shapiro, and Shalaika in the early 80s. And it's Guy Enyart checked that there is at most one correspondence which has all these properties. So the question was, does it really exist? And for small values of n, for n equals 2, it's checked by Kutzko. For n equals 3, I think it was basically checked by Guy, though I'm not sure that... Did you do all products? Not quite, but basically checked by Guy. And in both those cases, the proof was by making an explicit list of both sides and matching the things up and checking everything corresponded. Okay, I wanted to say a few more words about this. Well, I promised to tell you what an n-dimensional Frobenius semi-simple Wedelin representation was. So that should be a Wedelin representation, n-dimensional one, is a pair Rn, where R just a representation of the Weil group into GLN of the complex numbers with open kernel. Most naive continuity condition. N is just some n by n matrix, and they satisfy compatibility condition R sigma n. R sigma inverse is some scalar depending on sigma times n. And if you think about it a bit, you see that for given R up to equivalence, there are only a finite number of choices for n. So this is sort of some finite amount of combinatorial noise. It's not, in a sense, so. The guts of the matter is the R. Frobenius semi-simple just means the R part is semi-simple. So that's one comment I wanted to make. Another comment is that, sorry? This forces n to be unipotent, or nilpotent, rather. Oh yeah, so we had these special irreducible representations, and one can see those over on the Galois side. So it's also true, although I didn't explicitly state it here, that square integrable corresponds to the Wedelin representation being indecomposable. And the cuspidal corresponds to the Wedelin representation being irreducible, which means in particular that n is 0. And so that forces n to be 0. And so the only thing is an irreducible representation R of the Weil group. I guess there are various other compatibilities one would like in this theorem. It is known that this correspondence is compatible with the various instances of base change that had been previously established for irreducible smooth representations of GLN of K. One would like it to be explicit, so this theorem isn't explicit. There is Bushnell and Kutzko have given an explicit list of all irreducible smooth representations of GLN of K. Someone would like to be able to write down explicitly the corresponding Galois representation. We don't know how to do that, to the best of my knowledge. And I think that would certainly be something very useful to have. One would also like it to be compatible with any instances of global reciprocity that one has. And there the answer is basically it is known to be compatible with any instances that are known of the global correspondence. What else? Okay, well, there are certain reductions I want to mention right at the beginning. As 1980, Zelevinsky showed how to describe all describe all smooth representations of GLN in terms of the cuspidal representations of GLM for m less than or equal to n. And using that, he or maybe Rodier or something, showed that it was sufficient to establish the correspondence in this case. So the key case, and he did that by inducing from parabolic subgroups and decomposing the results. So the key case sufficient to get a correspondence between the cuspidal representations of GLN of K, irreducible cuspidal representations, and the irreducible n-dimensional representations of the Weil group. You can forget that capital N, that nilpotent matrix that came in. A second key simplification, and there are various ways of putting this, but let me choose one that's rather quick, is that I can define inside, actually I probably should have done that up there, inside the space of all cuspidal representations of GLN of K, let me write cusp prime to be those cuspidal representations which, after a finite base change, in the sense of Langlands, Arthur, and Clausel, becomes unramified. So let me just say potentially unramified. Of course, one would expect these, and one knows that these are in fact equal, but a priori I see no reason to, no easy way to know that. And Guy Eniar showed some other time in the 80s, later in the 80s, 88, that it is in fact sufficient to find a map from these potentially unramified cuspidal representations of GLN of K, we say onto the irreducible n-dimensional representations of the Weil group of K. Again, both these Ks with all these properties, so with properties 1 through 5. And if, once you find such a thing, then you first of all deduce that the cusp prime is just cusp. Every cuspidal representation is potentially unramified, and the theorem over here. He did this by dividing both cusp and ir-n into finite sets which had the same cardinality, and showing that any reciprocity map with these properties from one to the other would have to take each of those finite sets to the corresponding one on the other side. So you could then use a counting argument that there could be nothing, if you've already got a bijection here, there can be nothing in cusp which wasn't in cusp prime, because you've already, once you've got a Langlands correspondence here, there's no room for any cuspidal representation that isn't potentially unramified. So far, everything I've said is common to both our approach and Guy's approach. So now I have to either give two talks or choose one approach. although Guy's approach is very much simpler, I think we take about 270 pages, and I suspect Guy comes in under 27, so I guess it's better than a factor of 10 improvement. On the other hand, I think it's harder to explain in a quarter of an hour or whatever I've got left, so I'm going to mostly talk about what Michael and I did. Slightly paradoxical, but anyway, it does seem to be the case. And I'll mention from time to time, say something about what Guy did differently. So actually, I need a little bit of, put it over here, a little bit of notation. Because we're going to start working with L-adic cohomology and so on, I want to choose a prime L other than P, and I want to fix an isomorphism between the complex numbers and the algebraic closure of the L-adic numbers. And I want to define the reciprocity map with a slightly different normalization. Makes these statements 1 to 4 a bit more complicated, but it makes other things easier. So let me get it right. So if I look at the reciprocity map applied to pi joule tends to the absolute value of the determinant to the 1 minus n over 2, then that will be RL, or just, I really want an L, maybe just R of pi, and then I'm not going to worry about from now on what this n is. That was taken care of by Zalovinsky. Okay, so it's just the reciprocity map with this slightly different normalization. There's a joule and a twist by some power of the determinant. Okay, so the way Michael and I proceeded, there are 3 steps. We first of all define a map, a reciprocity map, from in fact, the whole of cusp to the irreducible n-dimensional representations of the Weil group. Then we showed that it's, and I'll come back to this if there's time at the end, how we did that. We then showed it's compatible with some global cases of reciprocity, if you like. And then we use this compatibility to then deduce local Langlands conjecture. And so Guy's approach was to remove A altogether, look at the global cases where we got compatibility, but just a very special subset of them, use that to these global cases where there wasn't full compatibility known to define, as it were, this reciprocity map and then prove, and then sort of simultaneously we'd sort of do B and C at the same time. Okay, so let me, I'm going to go through these in the order B, C, A, because A is longest and I might not have time for it. Let me first of all state the compatibility theorem due to Michael and myself, so that if pi, so let L be a CM field and pi a cuspidal automorphic representation of GLN, of the adels of L, satisfying firstly, that pi should be conjugate self-dual. C's complex conjugation, this is dual. Secondly, that its infinity type should be of the sort that should correspond to a nice Galois representation. So pi infinity, some people say regular algebraic, or same infinitesimal character as an algebraic representation of whatever it is, the restriction of scalars from L to Q of G of N. And finally, that at some, we need something like this if we're going to have Galois representations at all. And finally, that some technical condition that at some finite place, pi x is square integrable for some finite place x. And then the conclusion is, so then there is a continuous representation R of pi from the Galois group of L to GLN, say QL algebraic closure, such that, which is compatible essentially everywhere locally with the local correspondence that we defined in A. So such that for any finite place Y of L, we have this L-adic representation restricted to the Weil group at L completed at Y, up to semi-simplification. Semi-simplified is nothing else than what I was just calling over there R, which is this twisted version of the reciprocity map of the local component of pi at Y. And let me point out, because we didn't in our original version of the paper, but I've been told it has applications, that in fact, moreover, we know that pi is tempered at all finite places. So, moreover, pi y is tempered. Oh, sorry, I should say any finite place y not dividing L at this point for this compatibility. Of course, at L, things are much more complicated. Moreover, for here it doesn't matter, because we can change the L. Moreover, pi y is tempered for all finite places y. Okay, well, I should say a couple of things about this theorem. So Kottowitz and Clauzel proved a very similar theorem with a number of rougher edges here, most of which I don't want to go into. But crucially, they only determined such a relation away from some finite, unknown finite set of places. And in particular, they only got this at good places and not even at all good places, and just away from some unknown finite set of places that should have been good. Key thing here is that we really know it everywhere, in particular at the bad places. Okay. So if you suppose that you have some map, little r, or reciprocity map, defined in a way that I haven't at present explained, and that it has this global compatibility, it's not so hard, and it was explained by Michael Harris, how to deduce the local Langlands conjecture. You look at extensions of CM fields which are soluble but not necessarily Galois. And you consider characters chi, Grossen characters of the field, some non-Galois soluble extension of L, satisfying, as I say, it has to be algebraic and even further restrictions on the infinity type. And in those circumstances, Michael showed how you could attach to chi an automorphic cuspidal automorphic, well, maybe not always cuspidal, an automorphic representation of GLN, if this thing had degree n, GLN, via dels, of L, with the property that you can apply this theorem to it, and that R of theta of chi is nothing else than the induction from the Galois group of M to the Galois group of L of the reciprocity map applied to chi. And then you can look at so that you can do this uses two things. It uses Langlands Arthur Clozel base change, but that's not enough to do it in this non-soluble case. I mean, basically you want to go up to n and then descend. That gives you a series of cyclic things, but the descent, you usually lose information at each cyclic change. The point is that you don't lose information because you've got Galois representations at each stage, and you use that fact. So plus above theorem, or just the plus that the Cotowitz-Clozel version of this theorem suffices. And then you have an equality of L functions, the automorphic L function and the geometric L, or the algebraic L function, for these things. I will just write it for single ones, but you have it for pairs as well. So you have L theta chi of S equals almost everywhere, away from a finite number of places, L of induced of R chi. And both these things have functional equations. This has a functional equation coming from the theory of automorphic L functions. This has a functional equation coming from the fact that this is the same as the L series of chi. So this has a functional equation as well. The Galois side using some sort of invariance under Brauer induction. And when you have two L functions which are equal almost everywhere, and they have them and their twists all have these equalities like this, you can deduce the equality not only of the L factors everywhere, but the epsilon factors everywhere. So this implies 5 of the local Langlands conjecture, which is the hard part. So very briefly, what Guy did was, rather than defining the map, the reciprocity map directly, he took the Cotowitz-Clozel version of this theorem, applied it only to things that looked like theta chi, and just decreed the reciprocity map to be sort of what you got on the other side, and showed that it was in some way consistent no matter what theta chi you used. And then again, he could finish using Michael's argument. Okay, so I've got 5 minutes to try and talk about the first part, which was, where does this reciprocity map come from in the first place? So to do that, I want to sort of completely change direction. There's a unique one-dimensional height n formal OK module over the algebraic closure of the residue field of K, which I will call sigma n. And I want to consider the deformation theory of sigma n. So I want to consider the functor from complete local Noetherian OK algebras R with residue field K bar two sets, I guess, which sends R onto isomorphism classes of triples G, J, alpha, where what are all these things? G is Barsotti-Tate OK module over R. J maps our unique choice of 1 over K bar isomorphically to the special fiber of G, and alpha is a level structure in the sense of Drinfeld. And then this is, Drinfeld showed that this is representable over some ring that I will call Rnm. So n is, we're working with GLN, and m is how deep level structure is going. Okay. And this ring has an action of two groups. Firstly, the endomorphisms of this sigma n are just the maximal order in the division algebra dn. So this has an action of ODn cross, which is acting by varying the j, and it has an action of GLN OK mod pk to the m, which acts by composition with the level structure alpha. And so what I want to do is I want to take this ring. Oh, I also wanted to really tell you a special case. In the case n equals 1, R1m, this G is then a Lubin-Tate group. And here I just get the maximal, well, the ring of integers of the completion of the maximal unramified extension of K adjoin the pk to the m torsion points in the Lubin-Tate formal group. So this is exactly reduces in the case n equals 1 to Lubin-Tate theory. I want to produce a rigid analytic space so let me do that. Sort of generic fiber of this thing is a rigid analytic space. I want to take its étale cohomology in the sense of Bekovich. And then, as usual, one can take a direct limit over m. And that gives some space which has an action. Well, when I take a direct limit over, well, there's still this ODN acting. When I take a direct limit over m, I get an action of GLN of OK. And on here, the inertia group of K is acting compatible with this tensor product. I get an action of the inertia group of K. In fact, there'll be a slightly bigger group acting, but I don't have time to go into that. And then I want to take a virtual module. I want to take all the cohomology put together in this way. And let me call this virtual module psi n. And in fact, it's simpler if I take rho, an irreducible representation of the division algebra, then I'll define psi n the rho component to be just the homomorphisms as O dn cross modules of rho into this psi n. And then it turns out that once I've done this, the bigger action is easy to describe. This has an action of gln of k across the whole of the Weil group of k. And the theorem is that if pi is a cuspidor, we give a theorem in other cases, but it's slightly harder to state, so I'll stick to cuspidor. It's a cuspidor irreducible representation of gln of k. And if I take the part of this L-adic cohomology on which dn cross acts by, I first of all apply the Jacquet-Langlands correspondence to rho. Sorry, I'm doing this wrong. I take pi, I take its dual, and take the inverse of the Jacquet-Langlands correspondence, so I get an irreducible representation of dn cross, and take that component of this état cohomology. This is nothing but pi itself tensored with some n-dimensional representation of the Weil group of k. For some n-dimension. And although these things should all be virtual, this is in fact a true representation for some true n-dimensional representation of the Weil group of k. And that is how we initially define our correspondence and then show it's compatible with the global correspondence in this way, and then deduce it has the properties of the local Langlands correspondence. The proof of this theorem and of this theorem, they're carried out at the same time by analyzing the cohomology of a certain unitary group Shimura variety. And basically we show that the locally we can model the formal completion of that Shimura variety by these rings Rnm. And we obtain a formula relating the cohomology of that Shimura variety with its Galois action to the cohomology without a Galois action and the cohomology of these rings Rnm. And that formula is sufficiently self-referential. You can first of all show that the cohomology of these rings Rnm has to be of this form, and then once you've done that, you can deduce the compatibility everywhere with this particular R. Okay, so I should stop.
Are there any questions? Okay, yes.
So the unitary groups we're using are the ones singled out by Kottowitz, which have no endoscopy. So it disappears for the same reason as it disappears in a Kottowitz analysis. Well, they're two different papers, yes, but both of them use the same unitary groups which have no endoscopy, which is why they Kottowitz analyzes the cohomology of the corresponding Shimura varieties, and Clausel proves a base change theorem between the unitary group and GLN, which is why we can state a theorem about GLN at the top blackboard. But in fact, there is even in Kottowitz's analysis, he has to use a fundamental lemma that is known, a fundamental lemma for base change, which we avoid somehow. So we actually reprove Kottowitz's results. And somehow our method must be different from the Langlands-Kottowitz approach, because, for instance, we don't use the fundamental lemma for base change. Sorry? So we express the cohomology, we stratify the special fiber. And on each stratum, we write a formula relating the cohomology to the cohomology of what we call varieties, which are things that live only in characteristic P, and the cohomology of these rings RNM, which are sort of universal, independent of the global situation. Then the cohomology, then we count points on these varieties, and what you find is you get orbital integrals on inner forms of GLN rather than twisted orbital integrals on some other one. And so you use comparison between inner forms rather than.
Any other questions? Okay, let's thank our speaker again.